Let's have a look at the second um, video here. We're looking at a few things that are related to or directly impact this section. So what we're looking at here is we're looking at the idea of motion. And when we talk about motion, we're looking at all the different things or different factors that need to be addressed when we do the topic motion. Right? So the first heading or the first definition we need to work with is something called the frame of reference. So when we talk about the frame of reference, we're looking at our physical surroundings. And in our physical surroundings, everything around us is within reference to something else that's around us. Right? So it says here physics involves the study of our surroundings, a form of analysis where everything is put through a logical reasoning process and often provided a theory for. So when we talk about a frame of reference, we're talking about motion relative to something. And just ignore this dumb trick part. So let's say how fast does a bird or plane fly? So what we mean by a frame of reference is, are we talking from the ground? Are we talking from a building? How fast on a person on the plane is moving? People on the ground versus people in the plane. When we're looking at a frame of reference, we need to know, where am I at a certain point? So when I'm looking at the frame of reference, I'm looking at the origin point. Where did I start? So to analyze the motion of a body, first we need to find the location of the body at a certain instant of time. Location, time. To do this, we have something called a coordinate system. A coordinate system means that, just put this information down here. When I'm looking at the idea of the frame of reference, I have a y-axis and I have an x-axis. But running through my axes, let's say here and there, y, x, I have something called a z-axis. Right? And what this creates is a three-dimensional space. So when we talk about frame of reference, and it means that I can be within this three-dimensional space. I can be over here. Right? Oops. Let's have a look here. I can be over here for some moment. I can move here to the center. I can move here. So I'm moving around all of these places in a three-dimensional space at all times. I can move anywhere that I need to move. Now, when we talk about this movement, where are we starting? What's our starting point? So let's say, for example, when we were looking at the question with the rugby player. The rugby player, he stood over here. He stood here doing his thing, his rugby ball, right? This rugby ball player was pushed. He was pushed this way by two people, and he was pushed this way by two people. And when he was pushed from both sides, he had to move. He either could go forward or he could go back. And what we mean by that now is that this rugby player is the frame of reference. Right? And if we had to discuss this whole situation, if I had to put the team pushing the player as the frame of reference, then things would have been a little bit different. If we were looking at, let's say, this team here, then if this was the frame of reference, then this whole sum would have looked quite differently. So when we do physics, the earth is our frame of, let's just move this down, sorry. The earth is our frame of reference. Alright? So basically, it's us and we looking at it from our point of view. Everything in your life happens from your point of view. You leave home to go to school, but your friend also leaves home to go to school. But where you're both leaving from is a different point of reference. So when we talk about the point of reference, we're looking at where are you coming from? What's your coordinate? Because I said we're putting things onto these axes, it means if I'm here, I'm on a X and Y situation. If I'm over here, I'm on an X and Y situation. I'm at a coordinate. Where am I coming from is my frame of reference. Right. The next thing we're looking at is position. When we look at position, to describe the motion of an object, you must first be able to describe the position, which is where it is at any particular time. Let's get this out. The position, where it is at any particular time. That's what we need to know. All right. More precisely, we need to specify the position relative to the correct frame of reference. So when I talk about the position, I want to measure a location from a point of reference. Right. And this position is always going to be measured in meters. Right. And the symbol that we use, so this is the SI unit. And the symbol, the symbol is X. Right. So when I'm talking about my position, I want you to think about it like this. If I'm in a certain position and I say to you, come and find me. If you don't know where I am, what my position is, you will never find me. Also, if you don't know what time I was at that position, you also won't find me. Let's say I say to you, meet me tomorrow at school. That's it. Meet me tomorrow at school. What don't I know? Two things. Where and when. So in order to discuss something, I need to know, in order to discuss something's position, I need to know when it's happening and where it's happening. All right, so let's say I tell you to meet me in my class. All right. So here's my class here. All right, that's my class. I'm just giving you a bird's eye view of the situation. There's my desk, the lab desk, board, and then all of you are somewhere here, 1.5 meters apart. Let's say I tell you to meet me here at this position. But then later on, I move and I go to this classroom over here. This classroom has its board here and its desks are spaced out. The desk at the back here. Alright, so this is position Y. So what I've done is I started off here, but I ended up there. So what I did was I went from X to Y. I changed my position. So when I talk about a change in position, I started off from X and I ended up at Y. When we talk about a change, we use the symbol, and we've discussed this a little bit, a triangle It's a Greek letter, like this means theta. This is delta. And delta means change. And I know that position is the value x. So if I had delta x, I would have a change in position. So this is the symbol for change in position, and it is measured in meters. Oops, spelling. Meters, which is within m. Alright, so those are the two things, position and frame of reference. Let's have a look at the next definition. Alright, the next thing we're looking here at is distance and displacement. Now, we spoke about this a little bit. The first thing is distance. Alright, let's just talk about distance. Two things. The symbol is a capital letter D, and the SI unit is meters. Alright, little m. And we spoke before, and I said to you that when we talk about the distance, and I can see it here, look at this little boy. He went all the way from point A, and he traveled all the way to point B. All right, that's his first one. And then from B, he went all the way down here to C. And he did this kind of a thing. Right? That is his distance. Right? So when we talk about the distance, it is the total length of the path taken. This is important. Total length in meters of the path taken from one point to another. Right. We spoke about this before. I said that this is a scalar quantity, which means it must only have magnitude. It must have a size. Right. So I want you to think about it like this. Because we say distance is a scalar, I don't care what direction you're going in. So let's say, for example, if I look at the Comrades marathon, right? The Comrades marathon is from Pietermaritzburg to KZN. No, to Durban. Sorry. Oops. To Durban. Alright. So you start off here in Pietermaritzburg, and you run and you run and you run. You do the route, and you go all the way, and you end up here in Durban. Sorry. Right. You start here in Pietermaritzburg, PMB. Right. When you take that trip, you can take any route to get there. Not in the marathon, obviously. But if you go from Pietermaritzburg to Durban, you could decide to take this route. Right? But you still end up in Durban. It doesn't matter which direction you're going in. Right? But you get to Durban. So no matter which pathway you take, you're going from one side to the other side, and we're looking at the length of that pathway. Right? Now, if we had to bring the direction into it, I spoke to you guys about this. Right? And we talk about this being the displacement. And when we talk about the displacement, we are talking about, let's just go up here. I'm just going to move this out of the frame so I can get back to it just now. Right? So when I look at the next one, I'm looking at the displacement. Right? right? The symbol is delta x, and the SI unit is a little m. Now this is important because what is this symbol here? I hope you're noticing that it means the change in position, of an object, person, vehicle, etc. Dot dot dot. Change in position. All right. So what we're looking at here is, you also need to understand that the reason why we're using x here is because we're going to work in one dimension. Oops. What that means is, remember I showed you the x-axis, the y-axis, and the z-axis. We're only going to either be working on the x-axis or we're going to look at the y-axis. It's better for us to work just in the x-axis. So it makes sense for us to use delta x because it's a position on the, when we talk about the position, it is the position on the x-axis of a Cartesian plane. All right, and it must have direction. All right, so if I'm looking here, if an object moves relative to the frame of reference, for example, if I'm looking at this professor over here, she starts off here. That's where she was standing. And then she moves all the way to the other side. Oops. She was all the way to there. And she ends up at position number 2, which is here. Right. So if I'm looking at that sort of setup, her position has changed. It started off here and it ended up on the other side. Sorry. I almost did a silly thing. Oops. Sorry. Just going to line this up here. She starts off there. She ends up there. This is important. Right. So what we're looking at here is we're looking at the change in the position. Now the idea of change in position, and what we can write here, is that the change in position is equal to, I want to know how far she moved, right? So she started off here at 3.5. And then she moved, she started off here at 1.5 and then she ended up at 3.5. So to find that change, I can say, just do this. Oops. I'm going to give myself some space to work here. Right. I can say that I must take the final, so the displacement, the x final, so the final position, and I must minus it from the initial position. So how we're going to write it, we're going to say delta x is equal to final position, x final subscript, minus x initial, which is a subscript. Now the x final was 3.5 meters, minus the x initial, which was 1.5 meters. So if we pop that into our calculators, let me just move some things down here. Oops. I'm going to end up with 2 meters. So my change in position is equal to 2 meters. But because displacement is a vector quantity, so make a note here, it's a vector, I need two things. I need magnitude and I need displacement. Right. Magnitude, sorry, and direction. Right. So I've got the magnitude. It's 2 meters. The size of this distance, this displacement that's happened is 2 meters. And if I look here, it's to the right. Or I could have said east. Or I could have even said the best one is in the direction of motion. Right. So we're understanding here. You don't have to worry about that calculation over there. We're looking at our own type of calculation. So that O should actually be X initial. So this is also an important formula for us to remember. The word displacement implies that an object has moved, good, or has been displaced. 1 second. Oops. Although the position is the numerical value of x along a straight line where the object must be located, displacement gives the change in position along this line. So remember what I said, the line we're talking about is either along the x-axis, which is horizontal, and if it's along the y-axis, it's vertical. But we're going to look mostly at horizontal. Since displacement indicates direction, it is a vector, I said that, and can be either positive or negative, depending on the choice of the positive direction. Remember, we said we must choose. Another thing, if you get a negative value, it's moving. So let's do this. If you get a positive value, it's moving in the direction of motion. All right, so it's the one we chose as positive. If it's negative, it's moving in the opposite direction of motion. So remember with this one though, if it's ever negative, we must change to positive and then add in the direction. And that direction must always be opposite to the positive direction that we chose at the beginning. So that's the only way that this is going to work. Also, another point, please note that the displacement has a smaller numerical, I'm just going to move up here, smaller numerical value than distance because it is a straight line between 2 points. Right. So remember, we must understand what we mean by displacement. Now let's have a look at an example of displacement. All right, let's have a look here. So I've got an example here. And I've got a school and I've got Como, Colo, Cosma, Kohis, and Kevin and the shop. Please make sure you get this example into your books because we're going to be working with it actively. And each of these are 100 meters apart from one another. And we're going to look at some of the questions that go with this. All right, so let's look at the first question. The first question says, Kohis walks from Cosma to school. All right, so let's have a look here. I've got Kohis here. And Kohis is going to go to Cosma's house and then to school. So from Kohis to Cosma, we ended up here. That's the first move she made. Right. The second move she made is she moved from Cosma to school. So 1, 2, 3. Alright, so in total here, what they want to know is what's the displacement and what's the, oh goodness, what's the distance? Here's a highlighter. A distance, and they want the displacement. Alright, so let's have a look at this more logically. When Kokis walks, so let's look at distance. The distance. When Kokis walks to Korma, that was 100 meters. Alright, then when they went from Cosma's house, she went from Cosma's house all the way to school, which is 100, 200, 300. So plus another 300 meters. So her distance, or the length that she's walked, is 400 meters. Right? If we look at the displacement then, because displacement is a vector, first thing I have to do is make a decision. I'm going to say that anything that moves to the right is positive, and anything that moves to the left would be considered negative. So if I'm looking at Kokis, so Kokis is moving, so right means this way and left means this way. Kokis is moving to the left, isn't it? So she first moves 100 meters left, and then she moves another 300 meters, so plus negative 300 meters. So in total, Kokis has walked negative 400 meters. But we know the rule. The rule is that delta x, or any vector, must be a positive value, and we must include the direction. So if this value is negative, it means she's walking left. So we'll say 400 meters to the left. Or if I wanted to, this is an or situation, I could have used compass points and used north, east, south, and west. And I could have said anything that moves to the east would be positive, anything that moves to the west would be negative. And then technically, Kokis now was walking 400 meters in the western direction. So in this example, in example A, the frame of reference is Kokis's house. That's the frame of reference. The origin point that we're looking at as the frame of reference, where we're starting at, that is the reference point. So that's the first one, right? Let's look at B. B says, another color, right? B says, Kolo walks to Cosma's house, then to school. What is her distance and displacement? So I'm looking at Kolo. Right, Kolo's over here. And Kolo's going to go from her house to Cosma's house. Great. Then from Cosma's house, she's going to walk to school. So she went 100 meters to Cosma, 100 meters back past her house. Let's undo that. I'm going to do it in a dotted line. She walks back to her house, and then she walks to school. What's her distance and displacement? So this was A, and now we're looking at B. Alright, so let's look at Kolo's situation. Right, with Kolo, in terms of distance, Kolo walked 100 meters from her house to Cosma's house. Then she walked another 100 meters back to her own house. Then she walked another 200 meters to school. Right? So her total distance was then equal to 400 meters. That was her distance. Right, let's look at her displacement. Right, her displacement, if we're going to take anything that moves to the right, we're going to take it as positive. She first walked 100 meters. Right, plus she then walked back. So her first movement that she moved was positive because she moved to the right. Then she went back past her house. So that would have been plus negative 100. Then she walked a further 200 meters backwards to school, to the left. So plus minus 200 meters. So that's what it's looking like now. So if I pop all of that into my calculator, I'm going to get a displacement that is equal to 200 meters, right? And because it's, I'm going to get negative 200 meters. So that means that the delta x is actually 200 meters. And because it's negative, I'm going to say to the left. That was her movement. Now, if I think about this, right? Let's have a look here. What would we mean by displaced? In the second question here, Kolo's house is the frame of reference. So technically, when she went to Cosma's house, right? When she went to Cosma's house, and then she came back past her house, she actually cancelled out those two, that displacement, because here's where we're measuring it for. That's where she started. That's where she ended. And technically, if she ended up at school, from her house to school, that's only a distance of 200 meters, or displacement. She technically only displaced herself 200 meters to the left. So when we're looking at these types of questions, we're looking at trying to understand what we mean by frame of reference and what do we mean by distance and displacement. All right, let's look at the next questions. We've got here C and D. All right, I'm just going to move up a little bit, and I'm also going to bring in that question again so that I think we can see it a little bit more clearer. No? Oops. I'll bring it in now, sorry. Alright, I just want that situation back so that I can work with it. Alright, so the example that we're using is the exact same example, which is answering the next two questions. Let's go here somewhere. Alright. Excuse me. Right, we have the next one. The next thing that we're looking at is we're looking at, what's this person's name? Como. Where's Como? Right. Como is over here. Right. Como walks to the shop, then to school. What is his distance and displacement? Right, let's look at the first thing here. Right, so Como goes all the way to the shop. 200 meters, 300 meters, 400 meters, 500 meters, right? Then from the shop, he goes, so 100, 200, 300, 400, 500. Great. Then he goes, I'm just going to do this, 600, 700, 800, 900, 1,000, 1,100. So he went all the way to the shop and all the way back. So for C, in terms of his distance, we can say he went 500 meters and he ended up at the shop. Then from the shop to the school, a further 600 meters. So in total, the distance that Komal has walked is 1,100 meters. Great. But now we want to know, what is the displacement? So again, anything that is right will be positive. Anything that is left will be negative. So let's have a look here. Get a nice color. Right. What's his displacement? His delta x. Right. So first he moved to the right. So he moved, I'm doing this in pink. moved all the way to the right. You see that? So that was plus 500 meters. Great. Plus, at the shop, he then went back, isn't it? 1, 2, 3, 4, 5, 6, plus minus 600 meters. Alright, so if I pop that into my calculator, his delta x is then going to be negative 100 meters. But I don't like my answer in negative. I want my answer to be positive. So I'm going to say delta x is equal to 100 meters, and that negative tells me his direction. So which direction did he move? He moved 100 meters to the left. All right, so if I look here, Como was my frame of reference. He started here, so that was the start, and he ended up at school. That was the end. So technically he went, and if I look at it like in a little bit of detail, technically he could have just went, he could have went from his house to the left to school, and that would have just been 100 meters. And we can see that from the diagram that he only moved 100 meters away, right? All right, the last question says, question D. It says here, what reference points did you use for each of the above questions? All right, so if I'm thinking about reference points here, we use the reference point that is relevant. So we use the reference point relevant to the question. All right. The reference point is always where we start. Right? That is the reference point. Everything is in relation to that. So for C, for example, Komal's house was the reference point. Right. And that's how we look at this idea of distance. And you can see the distance. Look at that distance. That's how far he actually walked, the length of his distance. But the displacement is where you started and where you end up. What's the direct path of that sort of situation? Right? Let's look at the next heading, or the next concept. Also, don't forget, and I've actually forgotten for this whole thing, because delta x is a vector quantity, please make sure we put our half arrows. I'll make a note of it now. Whenever we write down that value, we must put in half arrows every time we see delta x. So even here, I should have put in, because that tells me that I have myself a vector quantity. So displacement must have that half arrow on top. It shows me that I have both magnitude. Oops, where's this thing? I must have magnitude, which means the size of something, and I must have direction. Please make sure you have all of these notes, taken down the definitions, the examples, you've worked through the notes, you've done these examples with Komal and Kochis and so on, so that you have a better idea of how all of this works. And you have a frame of reference in your book, so when you study, you can come back to something. Speed and velocity. Look at speed and velocity. The whole purpose of this thing is to hash out all the different variables that we'll be working with. So at this point, we've already looked at frame of reference, we've looked at position, displacement, and distance. The whole reason we look at all of that is so that we can get to this section and we look at these ideas of speed and velocity and how important they are, and knowing the difference between speed and velocity. So with speed, you've already worked with speed a little bit in the previous grades. So what we look at when we look at speed is we say that speed is the ratio of distance an object moves to the amount of time moving. Right, and if I'm looking at ratio, I'm looking at S is equal to D over T. The S here is speed. Please make sure you get this into your books, which is in meters per second. Distance here is in meters, and time we know is in seconds. And all of these things, speed, distance, time, they all are scalar units, right? So we not going to use this as often, right? It is not usable. Please don't use this type of formula. It's not usable. So if they ask you to find the speed, although you know that this is the formula, this is not the appropriate. You can use it in your personal space, in your home, on your personal time, if ever you want to work out the speed or the distance or the time. But in physical science, it is not an acceptable or appropriate formula to use. So I don't want to see this formula coming up. Right? I just need you to understand that we're relating things that happened previously in your previous years of schooling. We're relating it to that. Right? The next definition we look at, or the next idea we look at, is something called the average. Right. When we talk about the average speed, we're talking about if I have a certain distance that I traveled. So I'm looking at VAV is equal to the total distance that was traveled over the total time. All right, so when we're looking at something like this, I can say VAV, right, is equal to D over T. All right, where VAV is the average speed. Right, and you're going to be wondering about that V and what that V is doing over there. We'll get to that, right? It's also measured in meters per second. So your average speed is thinking things like, let's say I'm doing a cycling race. And I'm on my bicycle. Oops, that's too close. And I'm on my bicycle and I'm doing my bicycle race. And I'm riding up a mountain or whatever the case is. There's my seat. And there I go. I'm riding up the mountain. I'm going and I'm going to go and all the way. So I'm doing this cycling trip. And I'm moving this way. And at the end, I want to know what was my speed overall. So when we talk about average speed, it's the overall speed during a trip, right? So I look at the total distance of this mountain. Let's say it was 60 kilometers. And how long did it take me? Let's say it took me 2 hours. So when we look at the average velocity, we want to know what speed were you traveling at, or average speed, we want to know what speed were you traveling at on your journey. And I take my total distance over time. This distance is still measured in meters, and it is the total distance. And here time is still in seconds, and it refers to the total time that we're looking at. So when we look at this, look here, I said 60 kilometers. Don't forget, in 1 kilometer, I've got 1,000 meters. Please make sure that you go from kilometers to meters. We times by 1,000. And if I want to go from meters to kilometers, I must divide by 1000. And we only ever allowed to work in meters. So please make sure you convert. Don't just leave things for what they are, whatever you feel like leaving it as. It is not appropriate. Right, let's look at the next one. Just gonna change colors here to another color. All right, so the next thing we're looking at is we're looking at the term velocity. All right, so let's just remember two things here. Speed is a scalar, so it only needs magnitude, whereas average speed is also a scalar. It also needs magnitude. The next thing we're going to look at is called velocity. All right. Velocity is like speed, but with direction. Oops. So it must have magnitude, it must have a size, and it must have direction. Magnitude and direction, because velocity is a vector quantity. So when I have my answers, I must make sure that I write it with a direction. All right. So let's have a look at the formula for this. We can say that the average velocity is equal to the change in position all over the change in time. All right. When we look at this sort of situation, I need to write a formula. I know average velocity is VAV, but this time it has a sign over it, a half arrow. When I look at change in position, now we've done change in position. If I have a change in position, it means I have displacement. So delta x, which is, also a vector, all divided by the change in time. And remember what I said about the word change. If I want to show change, I must use the delta sign, which is a triangle. It's going to be delta x over delta t. So what we can say is therefore, before I go therefore, this is average velocity measured in meters per second. So meters, that's how we're going to say it, per second. All right. Delta x here is measured in meters, and it must have a direction. And over here, we've got time, which is measured in seconds. Don't forget, time is always a scalar, because I want you to think about it like this. You cannot go back in time. There's no such thing as negative time. So time will always be in the positive direction, always. That's why it's a scalar. I can't say I have negative 15 seconds left. There's no such thing. So make a note for yourself that time is a scalar always. That means if your answer is negative, if your answer is ever negative, then it will be marked as incorrect for time, if they're asking you to calculate that time. So our formula, please highlight it. We can say that therefore velocity is equal to the change in an object's position, right, over a change in the time traveled. Right, and that is your definition of velocity. All right, so when we have these types of answers, please make sure you include a direction, east or west or north, bearings, left or right, up or down, whichever the situation is. Please make sure that you use the correct formula. Now, often, and this is a bit of a silly thing, right? Often, they're going to say to you in this section, calculate the speed. All right, this is where things get hairy. Calculate the speed. Your brain's going to tell you that I must use S is equal to D over T. This is not an appropriate equation. Please make a note for yourself that even if they say calculate speed, what they mean is use this formula. I don't ever want you to use speed is equal to distance over time, because guys, that's grade 9. You're in grade 10 now. So when you're writing your formulas or you're doing calculations, you need to make sure you use appropriate ones. And there are some of you who don't listen, because in waves you did the same thing. I want you guys to please make sure that you take it seriously. It will be marked as incorrect if you use speed is equal to distance over time. Because this here is all scalars. Right? And we don't want scalars. We want vectors. So the only formula that you can use to calculate speed is this one. Do not get confused. All right. Let's have a look at the next definition that comes about. So we're looking at the next thing. Just moving all of that up. And the next thing is called instantaneous speed. Right? Instantaneous speed. Instantaneous speed, right? If I look here, so I'll do it in a highlighter, at this word here, it talks about something in an instant. So I want you to think about it like this. When we think of instantaneous speed, it is the magnitude, so the size of instantaneous velocity. So basically what we mean by that is when we're looking at instantaneous speed, we're looking at the change in velocity or speed, you can say that, or speed in a very small time period, right? I want you to think about it like this. If I'm driving, let's say I'm here, I'm at my home, I'm going from home, and I need to go to school. Right? I'm going to school. Right. When I go from home to school, let's say I'm going to get in my residential area. So I need to get out of my residential area. Right. When I'm driving in the residential area, I'm driving at 60 kilometers per hour. However, the minute I join the main road, I can start moving at maybe 80 kilometers per hour. But then I take the highway, and on the highway, I can go 100 kilometers per hour to about 120 kilometers per hour. Right. Now, if I look at this sort of situation, let's say I had to go from home to school, and let's say home to school was 6 kilometers, right? And that whole thing took me 20 minutes. right? Then if I want to know how fast I was traveling to school, I could use this information. But let's say over here, sitting here on the side of the road, as they usually do, because they have nothing better to do, is the police. And they measuring your speed in that zone there. And you traveling in that zone at 80 kilometers per hour. So in that moment, you are traveling at an instantaneous velocity or an instantaneous speed. It is over a very small time period. So when he measures you, he's only looking at you in maybe 0.1 seconds. However, the velocity of your trip changed. It went 60, it went 80, it went 100, 120, and then you go to school in 20 minutes. So that's over a longer period of time. That's what your speed was going to school. But when we talk about instantaneous speed, we're looking at a very, very small value. So if there's instantaneous speed, then there must be instantaneous velocity. Right? And when we talk about instantaneous velocity, we say it is the change in position, the change in position. It's the change in position in a small time period, right? Or let's say time interval. In a very small time interval where we can say the change in time for the velocity, because remember change in position, in brackets just put the delta x. The change in time is almost nearly equal to 0 seconds. So when we talk about instantaneous velocity, we're talking about very small time periods or periods of time where we can measure someone's speed. It usually works for speedometers. Speed traps with the police, they're measuring your instantaneous velocity. So that means you might have been traveling at a good speed. Just when you went past them, you were over the speed limit. Next thing you know, you have a ticket. And this is also measured in meters per second. Another way that you can actually look at all of this is if we look at this type of a constant, at this type of a situation, right? Right. So when we're looking at instantaneous velocity, we're saying speed at any instant. So if I'm looking at this diagram, this is how far, like I was saying, what the whole school thing is. Let's say in 1 minute I'm traveling from point A here to point B over there, right? And that over that time, I've spent quite different types of speeds. Let's say here I was going slow, and here I stopped. And I kept moving and I kept moving. Here I slowed down. Here I was moving at a constant velocity, right? And I traveled. Then, like I said, imagine the cop was sitting there and measures my speed here at point X. So in your trip, you might be going, and you can see it says 60 miles per hour. So mph is miles per hour. 1 moment and slowing down, stopping for a break a few minutes later. If I kept or checked my speed at any moment within a journey, that would be instantaneous in that moment. All right, so I hope that we understand this idea or these concepts right? It's very important that we make sure we have all the notes and the ideas written down into our books. All right, we're going to look at the last variable that we deal with in a little bit of detail. When we talk about motion, we can look at motion in three ways. I can have constant motion, or I can either speed up or I can slow down. Right. Speed up means I start at 0 meters per second and slowly I start to go faster and faster and faster. Or I could be going very, very fast and I start to slow down. Or I'm moving in a constant motion. Right, so when I talk about acceleration, right? When I'm talking about acceleration, I'm talking about these two. Either gonna speed up or I'm gonna slow down. So if I was gonna slow down, I would start at a speed. So here I'm starting at 0, but when I end up, my velocity is gonna be greater than 0 meters per second. When I slow down, my velocity is greater than 0 meters per second. But when I finally slow down, my speed or my velocity should be 0 meters per second. So that's what acceleration means. The symbol that we're going to use for acceleration is a small a with an arrow, half an arrow above it. And our SI unit is going to be meters per second squared. All right. So I'm going to write this down. Meters per second squared. Right. So what we mean by acceleration is that acceleration is the rate, this is important, of change of velocity. Right, and when we talk about rate, so I can say that acceleration is equal to the rate of change of velocity. Rate means time. And we know that velocity means speed. So it's going to be the change in velocity over the rate, which is the change in time. So I'm going to say A is equal to, remember change is delta, velocity is small letter v with a half arrow all over the change in time. This here is measured in meters per second squared. Velocity here is in meters per second and time here is in seconds. And those are the SI units, and that's your formula. Please make sure you highlight it. So what we mean here by change in velocity, have a look here. If I'm accelerating, I start off here at 0, point A, but at point B, my velocity is greater than 0, which means from here to here, from A to B, right, let's say A to B, there was a change in the velocity. It changes. The value at A and the value at B is not the same. So we're going to have a look at that in a little bit of detail. Right, another thing is acceleration is a vector quantity. If you haven't noticed, which means I need magnitude, which is size, which is usually a size, a numerical value, and I need direction, right? There are two types of acceleration. If I have a positive acceleration, right, that means we are speeding up, right? If ever because it's a vector, it can be positive and negative. If I have a negative acceleration when I do my calculations, then it means I'm slowing down, right? It doesn't have to just mean, negative doesn't have to mean in the opposite direction, right? What we choose, we must decide what we're choosing as the positive direction, what we're choosing as the negative direction. So when I'm looking at acceleration, I'm looking at situations like this. For example, if you have a look here, this person starts off slow, and then eventually, look at the dots, they go further and further apart. Here on the next one, look at the dots, they start out far apart and they get closer and closer together. So when we see a situation where it starts off slowly and eventually increases, it means I'm speeding up. In this situation, it's going to be, please make sure you get these examples down. It's going to be a positive acceleration. The next one starts off far apart, gets closer together. It's a negative acceleration. When we talk about negative and positive, we can even say negative is deceleration. Another time we can consider something to be accelerating is when it changes directions. So when we change directions, we also have a type of acceleration, right? Now let's have a look at this formula in a little bit. We're saying that A is equal to the change in velocity over the change in time. Now how do I get that change? And we looked at it before. How do I get something that has a change? So that means you start off with something, or let's say X, and then we end up with Y. So we looked at this when we did displacement and we spoke about what it means to change. So when I look at acceleration is equal to the change. Remember what I said is change. It's always going to be the final minus the initial. So for acceleration, I'm going to say V, velocity, the final velocity minus the initial velocity, all over the final time minus the initial time. So this is what your equation is going to look like in an expanded way. When I say V subscript F, I'm saying final velocity. When I say V subscript I say initial velocity. If I say T final, I've got the final time. So the time at the end. And when I say T initial, it's the time at the start of the whole thing. This is in meters per second. This is in meters per second. This is in seconds. This is in seconds. And your acceleration is still in meters per second squared. So that is what we mean by the idea of acceleration. Right? Very, very, very important. So this formula here that we're seeing, that's your main formula. Right? This formula that we're seeing is an expanded. Both formulas, you can get marks for both formulas. So just make sure that you understand that you can use either one. It doesn't really matter as long as for you it makes sense. All right, let's have a look at the summary. All right, if I'm looking at the summary of things, I'm just going to go through this stuff with you. Just bear with me. If I were you, I'd get the summary into your book. It's a better way of looking at things. Right, the first thing that we discussed was scalar units versus vector units. I know with the scalar, I only need, so I'm just going to use a pen to tick off here. You don't have to tick, you have to draw this whole thing. Got a scalar, only magnitude. Vector, magnitude, and direction. The next thing that we looked at is the type of scalars. We looked at distance versus displacement. We looked at speed versus velocity. What I'm looking at here in the center with the SI units, ms over here is meters per second. You can write it in two ways. That line in the middle just means meters divided by seconds. And for meters per second squared, you can say meters per second squared for acceleration, minus 2. Right, another thing we looked at is the frame of reference. If I look here, up here, can we see? We looked at if I have B, for example, as my frame of reference, then if I use A as my frame of reference here, then B is 5 kilometers right, and C is 2 kilometers left, which would be negative 2 kilometers. Don't forget, when we talk about displacement, it's this distance in a specific direction. Don't forget to consider your starting and your ending point, right? Velocity, rate of change of displacement, it's speed with a specific direction. So we came up with some formulas here, and we said that velocity is equal to the displacement all over the change in time, right? So those are some of the formulas. The other thing that we looked at is we looked at the difference between distance and displacement. We looked at speed is equal to distance over time. We looked at average speed. We looked at what's the difference between a distance and a displacement. So let's say, for example, if I'm looking here, it says given the journey A to C takes so much, you can say the distance 14 kilometers, but the displacement was only 6 kilometers. Right, let's just have a look here with this formula here. We know that acceleration is the change in time over, change in velocity over time, and that's how we get meters per second squared. Right, they use different symbols here. We using A is equal to VF minus VI all over change in time. Same thing. VF, another symbol that we can use is V. And VI, another symbol we can use is the symbol U. Either one is fine. We prefer these ones, but I'm going to show you what we mean by those ones as well. So different textbooks do different things. All right. When we talk about acceleration, this is very, very important. There's some examples. If you have a velocity that's increasing, you have something that's accelerating. So the acceleration must be greater than 0. So let's say I was accelerating 2 meters per second for 5 seconds, and I had my initial velocity. All I have to do is put that into my formula, and I can get my value here at V final is equal to 20 meters per second. The second one is if I'm decelerating, it's a negative acceleration. We call that a retardation. It means it's going in the opposite direction of what is normal to us. When we're looking here, its acceleration is negative 3 meters per second. Guys, that's another thing that's important. When we substituting, right? Oops. Oh, sorry. When substituting very important. We must use negative values even if we changed it to positive. Right? Let's say, for example, and I'm looking here at B. For B, can you see that the acceleration there is equal to -3 meters per second squared? This means that the acceleration is equal to 3 meters per second squared in the opposite direction of motion. Right? In the opposite direction of motion. That's all that it means. But when I put this into any formula, because it was in the opposite direction of motion, I must use the negative values. Very important. So if I look at that calculation, they're saying A is equal to VF minus VI all over T. And that the VI value is equal to 20 meters per second. Right. So I'm going to say A, which is -3, is equal to VF, which I don't know, minus VI, which is 20 meters per second, all over the change in time, which was 3 seconds. All right, I'll multiply both sides by 3 to get rid of it, and I'm going to have -9 is equal to VF minus 20, right? I'm then going to say VF is actually equal to 20 minus 9, which is actually 11 meters per second. Oops. And that's how I can manipulate the formula to find my, because we didn't know VF. All right. So please make sure that when you enter it into a formula, you use the correct units. All right. The next one is no change in velocity. So remember I said to you at the beginning, you can either have constant speed or constant velocity or constant motion, or you can have speeding up and slowing down. Now, if something is constant, we say there's no change in the velocity. So if something is constant, which means the acceleration is equal to 0 because it's not changing. Now, there's two ways that something can be constant. The one is it's at rest. That means it's not moving. It's at the stop state, or it's just standing still. And the other one is a constant velocity. So acceleration can be 0 at a constant velocity, which means there's no change in the velocity. I'm going to go into a little bit more detail with that kind of stuff, but please make sure you get the summary down into your books, and that you take down all the examples and you're writing notes and all the little pieces of information that I'm giving you. Very, very, very important. And the next video that you're going to look, so next up, we're going to be looking at graphs of motion. Now, please note here, I'm going to give you drawings, and I might include worksheets. Those worksheets, you have to, there's no option. You must print it. If you don't print it, you must draw everything out. I would highly recommend that if I give you a worksheet and I make reference to it, that you print it out. Go to the, if you don't have a printer at home, please go to Postnet or go to a printing shop. There's one in Columbine Square, there's one at that Panorama, there's one in Maysdale. Please make sure you go and get your stuff printed out so that you actually can work on these graphs. Otherwise, you have to draw the graphs out. Right? That's only if I give you a worksheet. Other than that, you're drawing all the graphs for everything. Right? And then you can move to the next video, which is going to be kinematics 3.